So now let us move on to the basic concepts of prestressing. So again, just like before, let's say for example, we have a concrete beam which is composed of infinitely many fibers, but we will just uh, uh, use some of those infinitely many fibers like these ones. And say for example, our concrete beam is just simply supported, and say for example, we have put a pre-stressing reinforcement at the centroid, along the centroid of the cross-section of the concrete beam. And due to this pre-stressing reinforcement, a compressive force is being applied to the concrete beam. So the type of pre-stressing on that situation, or on that scenario wherein the pre-stressing reinforcement is located at the centroid of the cross-section, is what we call concentric pre-stressing. So why is it called concentric pre-stressing? Obviously, because the pre-stress force P, acts concentrically or along the centroid of the cross-section. That's why it's called concentric pre-stressing. So if you want to investigate what is the effect of this compressive force to the concrete, if we want to investigate what are the internal forces or stresses acting inside the concrete beam due to the application of these compressive forces, all we have to do is again just cut the beam. Just have a cutting section along or along the concrete beam, transverse the concrete beam. So again, if we have a cutting plane traversing the concrete beam, we will have a we will have two segments, the left segment and the right segment. So we will just use the left segment and separate it from the concrete beam itself. So the free body diagram will look something like this. So again, if we have cut a concrete beam, we know for a fact that there is an internal force that will come out, and that internal force should balance this external force acting on the concrete beam. So it must act along this line of action, same line of action as this compressive force, same magnitude, but opposite in direction. So the internal force that will come out when we separate this segment to this segment will be this. So I just move the force from this part to this part, just for to have an open space here. So the internal force that will come out, that is acting on this cross-sectional area that balances this compressive force from the pre-stressing reinforcement, is this force P. Same magnitude but opposite in direction, and the line of action of this internal force coincides with the line of action of this external compressive force. So due to that compressive force, uh, it exerts, or I mean, due to that internal compressive force, obviously this is a compressive force because it points towards the member, the concrete member, so it compresses the member. And that compressive force actually produces what we call axial stresses. And we usually assume that those axial stresses acts as uniform along the cross-sectional area if the force is acting along the centroid of the cross-section, which is the case here. That's why we can call this axial force, because it acts along the centroid of the cross-sectional area. And if that is the case, the stress that this axial force produces is assumed to be uniform all throughout the cross-sectional area, with a magnitude of, from the strength of materials, we know that stress is equal to force over area. So if this is the force, and if we will call the cross-sectional area as simply A sub C, or simply A, or A sub C area of the concrete. Therefore, the magnitude of the stress, this uniform stress due to the axial force, will have a magnitude of force over area, or P over A, or A sub C area of the concrete, cross-sectional area of the concrete. So again, I have put a negative sign to indicate that this stress is actually a compressive stress. That is our sign convention. So that is the effect of the concentric pre-stressing to the concrete beam. It produces what we call internal stresses. Actually, it's called compressive stresses, which is uniform, which is a magnitude negative P over A sub C. Now, so for example, we will now take into consideration the fact that the concrete beam also carries its own weight in addition to the additional weights that it will carry, like for example, the superimposed dead load, live load, etc. So we will just call the summation of that self-weight or the dead load, the superimposed dead load, and the live load. Let's just call the sum of those three as simply W. So that W will be carried by that uniformly distributed load W will be carried by the concrete beam, therefore producing reactions here at the supports. So if we will look at the free body diagram of the lip segment, it will look something like this. And again, we know for a fact that this uniformly distributed load W uh, produces internal forces or internal force and moments at this particular cross-section of the concrete beam. And what are those internal force and internal moment? The internal force is a force acting along the cross-section. And that internal force, which is this, is what we call shear force V. That shear force is acting along this cross-section parallel to the cross-section. So again, just like what what I did here, I just moved the 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 drawing from this part to this part just to have an open space here. So along that with the shear force, another thing that is being produced due to the application of this uniformly distributed load is what we call bending moment. Although again, may I just reiterate that this shear force is actually the resultant of these shear stresses acting again along the cross-sectional area. Although again, we usually assume that these shear stresses are uniformly acting along the cross-sectional area, but has a magnitude of shear average or the average shear. But again, in real life, the shear force or the shear stress acting on the cross-section of this concrete beam is not actually uniform but varying with the maximum magnitude of the shear stress acting on the location of the centroid, and then it diminishes as you go to the top and bottom fibers, especially if this has a rectangular cross-section. So again, in addition to the shear force that is being produced when you apply a uniformly distributed load on the concrete beam, another internal force or moment that is being produced is what we call bending moment M. And again, that bending moment M tends to bend the concrete beam in this way, in such a manner that it will concave upward. And again, just like what I have said before, there is a surface here or a fiber here that experiences neither shortening or elongation. And that is what we call neutral surface or neutral axis if we will talk about the cross-sectional area. And again, just like what I've said before, if you will investigate, the fibers above the neutral surface experiences shortening. Therefore, they experiences what we call compressive stresses. These are actually flexural stresses because these are stresses resulting from the bending moment. And again, the fibers below the neutral surface, as you can see on the figure, experiences elongation. Therefore, they experience tensile stresses or tensile flexural stresses. due to this bending moment. So the diagram of the flexural stresses due to the bending moment looks something like this. So it has a linear diagram. We assume that it has a linearly varying magnitude, with the magnitude on the topmost fiber equal to MC over IG, or the gross moment of inertia of the cross-sectional area. So I think I don't have to uh, discuss this further, because this is just a review of strength of materials or mechanics of deformable bodies. We know for a fact from mechanics of deformable bodies that the flexural stress resulting from the application or resulting from the bending moments or bending moment is just equal to the product of M and C, which is the half of the, or should I say, C is the distance from the neutral axis to the topmost fiber, divided by the gross moment of inertia of the cross-sectional area. So that is the magnitude of this particular flexural stress at the topmost fiber. So again, I have put negative sign because obviously, since this is compressive stresses, we usually designate compressive stresses as negative. And then in the same manner, the magnitude of this flexural stress at the bottommost fiber is similar to this, MC over IG. Again, M is the bending moment, C is the distance from the neutral axis to this bottommost fiber. Although in this case, since we assume that the cross-sectional area is a rectangular section, therefore the distance from the neutral surface or the neutral axis to the top and bottommost fiber are equal. So we just name them C, divided by the gross moment of inertia. So for the moment of inertia of a rectangular section, so for example, it is BH cube over 12. B is the width, H is the height of the rectangular section. And again, we assign positive to indicate that this is a tensile stress. So again, tensile stresses points outward away from the concrete beam, and compressive stresses points towards the beam. It compresses the beam, and then this pulls the beam away from the beam or from the cross section. So you can see that uh, if we have not applied this concentric pre-stressing, just like what I've shown a while ago, if there is no concentric pre-stressing, therefore there is no axial compressive force negative P over AC. So we are left with the flexural stresses. If we did not uh, have a pre-stressing reinforcement here, tendency the flexural stresses that is being experienced by the concrete are this alone. MC over I at the top, MC over I at the bottom. There is a compressive stress at the upper portion of the neutral axis, and there is a tensile stresses at the bottom or below the neutral axis. And again, we know for a fact that concrete has a low tensile strength. Therefore, if it experiences a large magnitude of tensile stress, tendency is cracks will develop. So again, if cracks will develop, tendency, since concrete is a brittle material, the tendency is the crack will easily propagate from the bottom to the upper portion of the concrete beam, resulting to failure of the concrete beam. So that will be the case if we did not put a concentric pre-stressing. But then again, since we have put concentric pre-stressing, thereby producing this uniformly distributed axial stresses, therefore the total stress being experienced by this particular cross-section is the sum of these flexural stresses resulting from the bending moment and this uniformly distributed axial stresses resulting from the compressive force from the pre-stressing reinforcement. So if you will add this to, the result will look something like this one. So since this and this have same direction, they are both compressive stresses, they will just be added. So this diagram will be added to this diagram and will look something like this. But on the portion below the neutral axis, if we add this diagram to this diagram, they will actually be subtracted from each other, resulting to this kind, or to this figure or diagram. But if we will investigate this total stress acting on this cross-sectional area, if we will investigate this, you can see that the resulting tensile stress at the bottommost fiber is obviously less than the tensile stress at the bottommost fiber if we did not put a pre-stressing reinforcement, if we have no uniform axial stress here. It will have a lower tensile stress compared to this if we don't have this, the stress resulting from the application of the concentric pre-stressing. Now, if you want to find the actual magnitude of this total stress acting at the topmost fiber, this is just obviously this, which is this, negative P over AC, plus this, which is negative MC over IG. Or in other words, this total stress acting at the topmost fiber is just the sum of the axial stress and the flexural stress acting at the topmost fiber. So let us just call the total stress acting at the topmost fiber due to these flexural stresses and axial stresses as F sub T, flexural stress at the top, or simply stress at the top. So again, the total stress at the topmost fiber is just the sum of this stress and this stress. And in the same manner, the total stress acting at the bottommost fiber is obviously just the sum of this stress, axial stress, and the flexural stress. So let us just call the stress at the bottommost fiber as F sub B, stress at the bottom, or flexural stress at the bottom. So its magnitude is just the sum of this axial stress and this flexural stress. So again, as you can notice, since we have added a pre-stressing reinforcement or concentric pre-stressing on the concrete beam, we have minimized the tensile stress acting on the concrete beam. So from this large amount of magnitude of tensile stress due to the bending moment alone, we have minimized or reduced that magnitude from that magnitude to this magnitude thanks to this axial compressive stress that resulted from the application of the concentric prestressing. Therefore, if we have minimized the tensile stress acting on the concrete beam, tendency is it will no longer develop cracks. Therefore, there will be crack propagation on this concrete beam. So that is what happens when we apply pre-stressing to a concrete beam, specifically a concentric pre-stressing. Concentric pre-stressing, which is located, the pre-stressing reinforcement is located along the centroid of the concrete beam. This is the result. It is the resulting stress, given that the concrete beam is a simply supported beam and loaded with a uniformly distributed load. So we have achieved our goal. Obviously, we have minimized the tensile stress that is being experienced by the concrete. So from this magnitude, we have minimized it to this magnitude. But if you can notice, consequently, yes, we have reduced the tensile stress acting on the concrete from this magnitude to this magnitude. But if you will look to the topmost fiber, the compressive stress acting on the topmost fiber from this magnitude, it was increased to this magnitude. It was increased by this amount of magnitude due to that pre-stressing reinforcement. So that is the consequence of reducing the tensile stress on the bottommost fiber. There is a corresponding increase on the compressive stress on that topmost fiber if we apply concentric pre-stressing, wherein the pre-stressing reinforcement is located at the centroid of the cross-section of the concrete beam. That is the consequence. there will be an additional compressive stress being experienced by the concrete. Now, although we know that concrete has a large capacity to resist compressive stresses, we don't want to fully use that capacity or strength. We don't want to stress the beam to a compressive stress that will be approximately equal to its 28-day compressive strength. We don't want that. We don't want to have much compressive stress on the concrete as much as we don't want to have as much as we don't want it to have a much tensile stress. But if we apply concentric pre-stressing, uh, it is it will automatically increase the compressive stress acting on the topmost fiber if we apply concentric pre-stressing. That is the repercussion or the consequence of applying concentric pre-stressing. It will reduce the tensile stress, but at the same time, it will increase also the compressive stress acting at the topmost fiber. So we don't want we don't want that scenario. We don't want to have much compressive stress on the topmost fiber as much as we don't want to have much tensile stress on the bottommost fiber. So uh, how can we resolve that scenario? How can we how can we achieve our goal of reducing the tensile stress at the same time we are not putting much compressive stress at the topmost fiber? What is the solution to that scenario? So actually, the solution to that scenario is instead of applying concentric pre-stressing wherein the pre-stressing reinforcement is located along the centroid of the cross-sectional area of the beam, instead of locating on that centroid, we usually locate the pre-stressing reinforcement at a distance E from the centroid of the concrete beam, from the centroid of the cross-sectional area of the beam. So, instead of locating the pre-stressing reinforcement on the centroid of the along the centroid of the cross-sectional area of the concrete beam, we usually locate it at a certain distance from that centroid. Say, for example, distance E. Actually, E is called eccentricity. So we usually locate pre-stressing reinforcement at a distance E from the centroid so that if a compressive force will be applied to the concrete due to that pre-stressing reinforcement, uh, we will have a more acceptable total stress that will be being experienced by the concrete beam. Actually, this type of pre-stressing, unlike the concentric pre-stressing, this is called eccentric pre-stressing. So this is different from concentric pre-stressing. When we say concentric pre-stressing, the pre-stressing reinforcement is located along the centroid of the cross-sectional area of the concrete beam. But when we say eccentric pre-stressing, the pre-stressing reinforcement is located at a certain eccentricity or at a certain distance from the neutral axis or the neutral surface, which is this case, this illustration. This is eccentric pre-stressing. So now, if we want to investigate what will now be the effect if we have moved the pre-stressing reinforcement from the centroid or from the longitudinal axis to a certain distance E, we just have to again cut the concrete beam, put a cutting plane there, and divide the concrete beam into two sections or two segments, left and right segment. Again, we will just use the left segment. So the free body diagram will look something like this. So again, to balance this force, the compressive force coming from the pre-stressing reinforcement, there must be a force that must counteract that. That will be located or that will come out when we cut the concrete beam. And that particular force that will counterbalance this must be located uh, along the line of action of this force so that it will balance this force with the same magnitude but opposite in direction. So let us just call that force, internal force that will that will counter this external force when we cut the beam, as P also. So again, move P. I just move this force from this location to that location to just uh, have an open space here, a free space here. So that the line of action of that internal force acting on this cross-sectional area is coinciding to the line of action of this external force, the compressive force coming from the pre-stressing reinforcement, so that they will balance each other. So they have same magnitude but opposite in direction and same line of action. So again, this internal force is acting on this location at a certain eccentricity E from the centroid. Now, if you can recall from statics of rigid bodies, that force, we can move that force from this location to this location along the centroid of the cross-section. We can move that force according to statics of rigid body, given that we will also add the moment being produced by this original force to this line of action where we want it to be moved. So what is the moment being produced by this force to this location? So again, moment is equal to force times distance. If this is the force and the perpendicular distance is equal to E, therefore the moment being produced by this force along this line of action along the centroid of the cross-sectional area is just equal to P times the perpendicular distance, which is E. So the moment will just be equal to P times E. So again, I think we don't need to discuss further this method. We already studied this from statics of rigid bodies, how to move a force from one place to another. Every time we move a force from one place to another, we have to add the corresponding moment that it will produce to that location where we want it to be moved. So at this moment, since we already added the moment being produced by this force to this location, we can already remove this because we already moved it from this location to this location. So what will be the result? Now we will have an axial force because we move the force to the centroid, along the centroid. So you can imagine this force is actually acting on this centroid location. So now we will have an axial force because it is located along the centroid, and a moment with a magnitude PE. Now, this axial force obviously produces axial stresses. Again, axial stresses are uniform. We assume uniform as long as the force is acting along the centroid of the cross-sectional area with a magnitude of P over area of the concrete. Again, negative since obviously this is pointing towards the concrete, so it produces compressive force or compressive stresses. As well as, since we have a moment here, the tendency of this moment, this is actually the moment due to the eccentricity of the compressive force. So the tendency is this moment PE actually uh, bends the concrete beam. But unlike the bending that we have seen a while ago, it bends the concrete beam in an opposite manner. So if a while ago, the moment that we were talking about bends the concrete beam in such a way that it will concave upward, this particular eccentric moment will bend the beam. This particular eccentric moment resulting from the compressive force will bend the concrete beam on a opposite manner. It will concave downward. So therefore, the flexural stresses that this moment PE produces uh, has compressive stresses at the bottom, since obviously the bottom part or the bottom fibers below the neutral axis experiences shortening, while the fibers above the neutral axis experience elongation. So therefore, at the upper portion of the neutral axis, the flexural stresses that being experienced by the concrete, since elongation is the since the fibers on the upper portion of the neutral axis experiences elongation, therefore the stresses acting on the upper portion of the neutral axis is tensile stresses. So therefore, they are pointing away from the concrete. So if this line is the cross-sectional area of the concrete, therefore the tensile stresses will point away from the concrete on the upper portion. On the lower portion, since there is shortening, therefore the stress that being produced or experienced at the lower portion is compressive stresses. So the resulting flexural stress diagram from this eccentric moment will look something like this, with the magnitude on the topmost fiber equals to, just like the formula for the flexural stress due to moment, which is mc over I. The flexural stress due to this eccentric moment, due to the eccentricity of the compressive force, will also have a magnitude of mc over I. Although the m, we will just change the m into, instead of m, we will change m into PE, because it is the moment that produces this particular flexural stress. So it has very similar formula to the flexural stress being produced by the service loads. And again, since the stresses on the upper portion of the neutral axis is tensile stresses, we have to put positive sign on this outermost flexural stress on the topmost fiber. In the same way, the compressive stress acting on the bottommost fiber will have the same formula, mc over I, wherein we just have to change m into PE, because again, it is the moment that produces this particular flexural stress. Again, we have put negative because these stresses are compressive stresses pointing towards the concrete beam. So these are the stresses that results when we apply eccentric pre-stressing. There is an axial stress, and in additional to the axial stress, there is an additional flexural stresses that results due to the eccentric moment from the eccentricity of the compressive force. Now, if the concrete beam will now carry the transverse loads that it is intended to carry, like for example, its self-weight and then the superimposed dead load and live loads. So again, let's just call the summation of those loads as simply W. So again, it will produce reactions, obviously. And if we will look at the free body diagram, uh, due to that applied uniformly distributed load, again, there will be internal forces being produced inside the concrete beam on this particular cross-section. And again, what are those internal forces or internal moments? Obviously, this applied load will produce a shear force on this particular cross-section, which is this, which is again, that shear force is the summation of the shear stresses acting on the cross-sectional area. And we assume that the shear stresses acting at the cross-sectional area are constant with the magnitude of shear average. But again, in reality, it's not constant. It varies with the maximum magnitude on the location of the centroid and then diminish as you go to the top and bottom fiber. If most especially if the concrete has a rectangular cross-section. And in addition to that shear force, another thing that this applied load produces at this particular cross-section of the beam is the bending moment. So let's just call the bending moment as M. And again, that bending moment, just like this one, that bending moment produces flexural stresses, just like what I have shown before. So again, we already know the flexural stresses that is produced by this applied loads. It produces compressive stresses at the upper portion of the neutral axis, while tensile stresses on the below the neutral axis. With the maximum magnitude of flexural stress on the top equal to mc over ig, m equal to the magnitude of the bending moment. And again, since it is compressive stress, we have put negative, while on the bottom, since tensile stress, we have put positive sign. So now, these are the stresses that is being experienced by the concrete at this particular cross-section. We have flexural stresses coming from the bending moments that is produced due to the application of the applied load W. We have axial stresses due to the compressive stress coming from the prestressing reinforcement, as well as a flexural stress coming from the eccentric moment produced due to the eccentricity of the prestressing reinforcement. So now, if we want to look the total stress being experienced by the concrete beam at this particular cross-section, all we have to do is add these separate stresses. So we just have to add them, and the result will look something like this one. The result will look something like this one. And if you want to find the magnitude of the stress at this topmost fiber, obviously, just like what we did before, the magnitude of this stress is just the sum of this stress, which is this stress, which is this, and this stress, which is this, or in equation form, it will have this formula. So again, let's just call the total stress at the top fiber as F sub T, flexural stress or stress at the top fiber. So again, that total stress acting at the top fiber is just a summation of the axial stress, which is this, the flexural stress coming from the eccentricity of the compressive force or the prestressing reinforcement. So it has a positive sign, so you have to include the positive sign. And lastly, the flexural stress due to the applied load. So you have to include the sign. So that is how you find the total stress acting on the topmost fiber of the concrete. And in the same manner, if you want to find the flexural stress, total flexural stress acting at the bottom fiber, just have to add the effects of this axial stress, this eccentric flexural stress due to eccentricity of the compressive force, and this flexural stress due to the applied load. So in equation form, it will look something like this. Negative P over AC plus this negative sign plus this positive MC over IG. So again, by just merely looking at this total stress being experienced by the concrete beam, when we located the pre-stressing reinforcement from a distance from the neutral axis, by just merely looking at this, we can see that we obviously reduce the tensile stress being experienced by the beam from this magnitude. So imagine if we don't have a pre-stressing reinforcement. So we will not have this one and this one. We will just have this one, flexural stress, if we don't have a pre-stressing reinforcement. But since we have put the pre-stressing reinforcement at this particular eccentricity, from this magnitude of stress, tensile stress, we have reduced this magnitude of tensile stress from this to this. So, due to the application of pre-stressing, we have reduced the tensile stress being experienced by the concrete from this magnitude to this magnitude, as well as the compressive stress. So, if you will look the compressive stress at the topmost fiber, total compressive stress, you can see that it not differs largely from the original compressive stress. Actually, sometimes this total compressive stress acting at the topmost fiber usually is less than this original flexural stress acting on the concrete beam. So obviously we have achieved our goal. And what are those goals? First is to minimize the tensile stress being experienced by the beam. So obviously we have minimized it. At the same time, we have not put additional compressive stress on the topmost fiber. We have not added much compressive stress at the topmost fiber. We might even decrease the magnitude of compressive stress acting at the topmost fiber as we decrease the tensile stress acting at the bottommost fiber. So if we will compare that total stress coming from eccentric pre-stressing to the total stress coming from or resulting from concentric pre-stressing, you can see that we just not reduce the tensile stress, but obviously we have got a much smaller tensile stress compared to concentric pre-stressing, as well as much smaller compressive stress compared to the compressive stress resulting from the concentric pre-stressing. So this is the advantage of eccentric pre-stressing compared to concentric pre-stressing. So from now on, as we go on with our course, you can expect that most of our uh, pre-stressing uh, configuration will look something like this. We will usually have uh, the location of the pre-stressing reinforcement at a certain distance from the neutral axis. We will not use this. We will not use the concentric pre-stressing because, again, as I've said, just like what I'm saying, there are negative effects when we use concentric pre-stressing. Yes, we can reduce the tensile stress acting on the beam, but at the same time, we have increased the compressive stress acting on the concrete beam if we have used concentric pre-stressing. But if we have used eccentric pre-stressing, we can reduce the tensile stress acting on the concrete beam, as well as we can also reduce the compressive stress acting on the concrete beam. If we cannot reduce it, uh, maybe the worst scenario will be we can just retain the compressive stress. Eh, so if we cannot reduce it, the worst case will be we can retain the compressive stress acting on the concrete beam. We will not increase it, just like what happened here in concentric pre-stressing. We have an increase in compressive stress. So that is the basic concepts of pre-stressing. That is the reason why we usually want concrete to be pre-stressed to reduce the tensile stresses as well as the compressive stresses in some cases. But the main purpose is to reduce the tensile stresses being experienced by the concrete, especially since we know that concrete has a low tensile stresses. So we want to prevent the scenario of there will be cracks that will develop on the concrete if the tensile strength, if the tensile stress exceeded the tensile strength of the concrete. So that is the basic concepts of pre-stressing. So we already addressed our fourth goal, which is to understand the basic concepts of pre-stressing. So just to summarize all of these things that we have discussed, let us just have a recap of what we have studied. We have known that pre-stressed concrete design is the design of concrete structures which have been introduced to internal stresses prior to carrying of total intended load. That's why it's called pre-stress. To counteract with a purpose, the purpose of that pre-stressing is to counteract the stresses that will result from this applied load. Then, we have studied the advantages of using pre-stressed concrete. We have known that if we are using pre-stressed concrete, the tendency is we will have a shallower depth, less maintenance, possible longer working life, lighter foundations, and good for long spans to reduce cracking and long-term deflection. But uh, Consequently, there are some disadvantages on using prestressed concrete, which are there might be higher costs due to higher quality of materials, as well as there will be an added cost due to the prestressing operations, and there will be more complex formwork due to the complex geometry of the sections. And then we have studied that prestressing started in 1872 when P.H. Jackson, an engineer from California, patented a prestressing system that used a tie rod to construct beams or arches from individual blocks, but was not really successful due to the existence of time-dependent prestressing losses, which were addressed as technology of materials advances, particularly prestressing steel, together with accumulated knowledge in estimating short and long-term losses. And lastly, we have studied that prestressing induces stresses that will counteract the stresses that will result from applied loads. So that is the main purpose of pre-stressing. So that's all for this discussion. Thank you for listening. If you have any questions, clarifications, or any other concern, please do not hesitate to contact me via, you can contact me via discussions on the Canvas, on our Canvas course, or you can message me on Facebook Messenger. Just search my name, Adam Stress John Nuevo Junicio, or you can email me via Google at arjunicio.ca@tip.edu.ph. So that's all for this discussion. Thank you and have a good day.